Alright, let's look at the graph of the other 4 trig functions. So we've seen sine and cosine, and we're going to look at the other 4. So we're going to start off with the tangent. Remember, tangent is the sine divided by the cosine, and we're going to plot the known points that we have down here. So when x is 0, then y is 0. Okay, sine of 0 is 0 divided by cosine of 0 is 1. 0 over 1 is 0. So the tangent is equal to 0. Alright, and then at pi over 6, alright, 1 pi over 6, we get the square root of 3 over 3, which is about 6/10. So about right, somewhere right there. Alright, and then 2 pi over 6, which is pi over 3, we get the square root of 3, which is about 1.7, so about right there-ish. Alright, and then right between those two, between 1 pi over 6 and 2 pi over 6 is pi over 4. We get a tangent of 1, about right there. Alright, it kind of looked linear for a second, but then it's starting to bend upwards. Alright, 3 pi over 6, that's the same thing as pi over 2. At pi over 2, we get the sine of pi over 2 is 1. The cosine of pi over 2 is 0. 1 over 0, that's undefined. We can't plot anything, that's infinity. Now, what's it heading off to? Well, what we got is, we've got like some 75, this is 90 degrees, so we've got 75, 85, 89, and something really close to this pi over 2. And we're seeing what's happening is we're getting higher and higher and higher and higher and higher as we make our way up. So we're getting at 3.7 and then 11.4. We're way off the grid. So we're just getting higher and higher and higher. And what's happening is we are hitting a vertical asymptote right here at pi over 2. Because again, you cannot divide by 0. So at 3 pi over 6, same thing as pi over 2, we're getting a vertical asymptote. This thing is going up, getting closer and closer and closer to infinity. Now think about it on the unit circle. So remember, on the unit circle, the tangent was the slope of this red line segment that connects the origin to any point on the circle. So as that thing increases, this is the slope of that line that we're getting. Alright, it's the y coordinate divided by the x coordinate. And the slope keeps increasing until we get all the way up to virtually a vertical line. And we're taking off towards infinity, and that's what we're seeing right here. We're seeing that slope is getting higher and higher and higher, and we're taking off towards an infinite slope. And if we keep going up, we go all the way up to a vertical line segment, which is an infinite slope. So you can't you can't have an infinite slope. And remember, tangent is also the y coordinate divided by the x coordinate. So 1 over 0, we're dividing by 0. You can't do that. So that's why we're getting a vertical asymptote right here. Okay. Now, what's going to happen when we go down into the negatives instead of going up? If we were to go down this way, if we were to go down instead of rotate up, go this way and do it, that would be a negative slope. And it's going to be a negative slope that gets more and more negative until it goes all the way vertical. So as we make our way in the negative direction, we're going to see all these same points again. It's just in the opposite direction. So negative pi over 6. Remember, sine of a negative is a negative. Cosine of a negative is like the positive version of that number. So we end up with a negative divided by a positive, which is a negative. So we're going to get the same outputs because it's positive sine divided by positive cosine when we're going this way. But as we make our way to the left, it's a negative sine of the same number divided by a positive sine of the same number, and it's giving us these negative, the opposites of these. So we're going to get at negative pi over 6, we're going to get that negative 0.6. The same thing that we got before. Alright, at pi over 4, we got 1. So at negative pi over 4, we're going to get negative 1. Alright, at pi over 3, we got 1.7. At negative pi over 3, which is negative 2 pi over 6, we're going to get negative 1.7. Alright, and then same thing as before. I'm going to get a number that's getting really close, or really big, I should say, the closer I get. So at like 75 degrees, I'm going to get something that's like 3.7. But again, if I make my way all the way to negative pi over 2, I'm going to get an asymptote. Now we've already talked about the period of the tangent function. The period of the tangent function is pi. And if you look, we're negative pi over 2, positive pi over 2. There's pi. So what's going to happen is we're going to see this repeat over and over again. So here's another period of it. If I just stack up the asymptotes and make that point right on pi, that has to be close enough. There's another period of it, and again you can do it again and again and again, just like with sine and cosine that we saw before. We can just keep repeating this, and we're going to keep having this pattern over and over again that we saw before. Alright, and then connect the dots. These are kind of look very much like cubics, like the graph y equals x cubed. But again, they're not, because they have these vertical asymptotes that the cubic function does not have. They have that same look to them because they are odd. The tangent function is an odd function, just like y equals x cubed is. Alright, so anyway, that's what they look like. They would keep going. There'd be another one out here. There'd be another one here. But they have that same cubic looking pattern over and over and over again. The tangent function does. Now, if you were graphing this on a graphing calculator, one of the bad things about these older graphing calculators is they don't handle vertical asymptotes very well. So if you did y equals tangent x and did your zoom trig, you're going to see they actually draw the vertical asymptotes in there instead of them not being there, which they're technically not there. So I would recommend for tangent, secant, cosecant, all these other ones that we're going to talk about today, to use Desmos, because it will just look better. So anyway, here's the tangent function, negative 2 pi, over here to the other side, positive 2 pi. So we're going forward 1 revolution, we're going back 1 revolution, and we can see that pattern. We don't see the vertical asymptotes at pi over 2 and 3 pi over 2, negative pi over 2, because they're technically not there. Okay, you can click on here and you get some points that are on the graph, as many as you need, okay, to help you plot it. But this does a much better job, much more accurate job, because again, there are no vertical asymptotes that are actually visible on the graph, and this makes it look like they're a part of the graph. The old TI calculators would connect dots between points that they plot. So they plot them one way up here, and then they plot another one way down here. They connect the dot. So we saw the location of those vertical asymptotes. But just know they're not a part of the graph. So the tangent function has this look. It's parallel. It kind of looks very similar, like parallel cubic functions that are just never crossing one another. Alright, the graph of the tangent curve, its characteristics, the period is pi, as we just said. The domain is all reals except the odd multiples of pi over 2. So what does that mean? That means multiplying pi over 2 times 1, 3, 5, 7, 9. So 1 pi over 2, 2 pi over 2, 1 pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and then the negative versions of those numbers. The range is all real numbers. Like everything gets hit in just one in between 2 vertical asymptotes, just one period of tangent, you hit everything. And again, think about the unit circle. That should make sense because we're talking about the graphs. Sorry, we're talking about the possible slopes. So there's positive infinity, there's negative slope all the way down to negative infinity, and then some positive slopes. Right? Sorry, positive slopes in here, all the way to positive infinity. So we go from negative infinity to zero slope to positive infinity in just one period, meaning pi radians. So our range is all real numbers. We're hitting them all within that one period of pi. Alright, vertical asymptotes at odd multiples of pi over 2. That's the reason why the domain has those as the exceptions. X-intercept occurs in the midway point between the consecutive asymptotes. So you can find your odd multiples of pi over 2, and then the even multiples of pi over 2, 2 pi over 2, which would be pi, 4 pi over 2, which would be 2 pi, 6 pi over 2, which would be 3 pi, right? Or 0 pi over 2. Those are all even numbers, even multiples of pi over 2, or just multiples of pi, right? 0 pi, 1 pi, 2 pi, 3 pi are all going to be the x-intercepts. Alright, it's an odd function like we said before. It's got origin symmetry like the cubic functions do. And remember, origin symmetry means that if AB is a point on the graph, so this would be a point on the graph. If you go back through the origin and out that same distance, then negative A, negative B is a point on the graph. So it does have origin symmetry. It is an odd function. Alright, and then the points on the graph a fourth and 3/4 of the way between consecutive asymptotes have the y coordinates of -1 and 1, because those are like pi over 4, right? Negative pi over 4, right? And then that's another, cycle around, so that's pi over 4 beyond a horizontal slope, and negative pi over 4 back behind a horizontal slope. At each one of these horizontal slopes, remember these are slopes with the tangent function. And remember the slope when we're at pi over 4, negative pi over 4, we're on the line y equals x, we're on the line y equals negative x, and the slope was 1 and -1 respectively for those two. So that's why we're seeing that pattern of the 1 and -1 as well. Alright, so same thing as before when we're graphing variations of the tangent function. It's the same thing as it was last time. So we've got all these different things. What do they do? Well, A is like a vertical stretching device. It makes the tangent function get pulled up or down by a factor of A. So if we zoom way out, when I make this thing bigger and bigger and bigger, it almost looks linear because it's stretching so high up, and it's kind of pulling that bend out of there that we see pretty drastically as A gets closer and closer and closer to 1. Remember that there's a subtle little bend there, just like with the cubic function. That thing gets exaggerated as we make our way down towards 0. We start to see it more and more, and then it almost goes away virtually. It looks like a bunch of parallel lines if we make A very big, because we're multiplying the output by whatever A is. So when this gets big, we're taking the output of the tangent function and making it even bigger. And so everything gets stretched vertically. Okay. B, that's going to do just like before. That's going to affect the period. So if we make it big, everything squeezes in. If we make it small, everything stretches out. But that affects the period. If we go into the negative, it flips over the y-axis and looks like it's going downhill instead of uphill, left to right. Alright, the same with A. If we flip it into the negative, it flips over the axis and does the same thing. Flips over the x-axis, whereas B causes it to flip over the y-axis. Okay, can't tell because the sign change, the odd function, the nature of the function. And then C is the shift, the phase shift that goes left or right that we were talking about. And then D is the one that moves us up and down. So same thing as before. It's just different variations, different shifting, vertical for D, horizontal for C, and then these are just stretches. Stretches or compresses in the either horizontal direction, so everything's being squeezed in, or the vertical direction, everything's being squeezed down, if we go down with it, or being stretched up. So it's the same thing as we saw before, it's just being applied to the tangent function. Alright, the way that we're going to handle this, the easiest way to do this, is to find your vertical asymptotes. The bx minus c is what's causing us to shift horizontally, and when we shift horizontally and compress horizontally, which is happening in here, like we saw, well, that's going to affect the horizontal asymptotes. Alright, so this, remember, tangent we can't put in pi over 2 or negative pi over 2 in a tangent, because that will cause us to have vertical slopes. So whatever bx minus c is, it has to be between those two for us to be able to get graph. And that's where this is coming from. But when we solve this thing for x, we find the vertical asymptotes, consecutive vertical asymptotes. Alright, so that'll find our vertical asymptotes. We'll solve that thing for x, and then the x-intercept is halfway between those two. Okay, we'll always find out the halfway between the points, the vertical asymptotes, and then halfway between the intercepts in each vertical asymptote is something that corresponds to a, not necessarily 1 or negative 1 anymore, but a and negative a when we find those quarter points. Okay, and that'll be one period, and we can do as many periods as we want, to the left and to the right, to get as many cycles as needed. Alright, so I've got this tangent function, so I got y equals 2 times the tangent of x divided by 2. So what we're going to do is, remember that x over 2, that is our b. b is the number that's being multiplied by x, so b is 1/2. So I'm going to take the x over 2 and set it equal to negative pi over 2 and positive pi over 2. And that's going to start us off. So x over 2 equals pi over 2, and technically, because that would be the same thing I would solve. There's nothing I'm adding here. That'd be the same thing I'd solve for negative pi over 2. So I could put like a plus minus in there and solve this thing. So anyway, doubling both sides, I would get x equals plus and minus pi. And that means that those are the locations of the vertical asymptotes of this thing. So I'm going to pull up a vertical asymptote for right here at negative x, and I'll get another vertical asymptote over here at positive x. Alright, and notice there is a period of 2 pi between those. So 1 pi right there, another pi right there. So all the way over here at 3 pi would be the third one. So that's a 2 pi in between. So there's a gap of 2 pi in between each one. Now, there is no vertical shift. There is no horizontal shift. So the original x-intercept is 0 is going to be there, but it's also halfway between the two asymptotes. Halfway between these two asymptotes is 2 pi. Right, and then remember, halfway between the asymptote and the intercept are the whole number points, or numbers that correspond to the amplitude, or not amplitude anymore, a number that's out in front of the tangent function. So at negative pi over 2, that's halfway between these two. Because it's a positive number, we're still going up left to right. So halfway between there, I'll go down to negative 2. Alright, and then halfway between these two, I will go up to positive 2. Alright, and the same thing, halfway between these two, I'm going to go down to negative 2. This is the second period. We've already got one full period. So that's what this thing's going to look like. That kind of gives me an idea. And then I just come in here and connect the dots. I'm going down towards the asymptote on the left side. I'm making my way up across the axis and up this way on the right side. Okay. So again, you can graph this and verify, just like we did with the cosine functions. I can put in 2 tangent x over 2. Alright, and then I can make my window go from negative pi to 3 pi, and make my tick marks pi over 2, the way I have it written on here. Alright, and then make my y minimum. It looks like negative 4 and 4 is good again. And graph that thing. So again, this calculator that's showing a vertical asymptote, vertical asymptote, vertical asymptote right along the edge. I can hit trace. I can tell it to plug in 0. I should get 0 out. If I plug in negative pi over 2, I should get negative 2 out. Anyway, you can use this to verify just like we did with the cosines to make sure we've plotted it right. Alright, let's look at one that's got a vertical shift in there as well. So it wants us to graph 2 periods of this. Remember, this is affecting the period. This is our bx minus c. That's what we're going to set to be equal to, or sorry, in between negative pi over 2 and positive pi over 2. So that's going to result in us having to add pi over 6 to all these places to isolate the x to be able to have the location of the asymptotes. Now remember, with your calculator, if you're doing this, it's easiest to leave off pi. So if I did negative a half, and it's also fine if you just do this by hand, but negative a half plus pi over 6, I'm going to add 1 over 6, and then math into a fraction. That's negative pi over 3 is our left vertical asymptote. And then our right vertical asymptote, this is 3 pi over 6 plus 1 pi over 6 is 4 pi over 6, which reduces to 2 pi over 3. So there is our second vertical asymptote. So I'll put those on there at negative pi over 3 and positive 2 pi over 3. So there's one period of this thing. Oops, this should have been a negative pi over 3, sorry. And then we're going to do that same thing again. Notice this is negative pi over 3, this is 2 pi over 3. That's a period of 3 pi over 3, or pi. So if we add pi, or 3 pi over 3, to our upper number here, 2 pi over 3, if we go another period of pi, we'll be at 5 pi over 3. Alright, so there's one period, there's a second period. They want us to give 2 periods. Alright, now halfway between these two, if you count, there's 1, 2, 3, 4, 5, 6 marks. Alright, halfway between that would be 3 marks, so 1, 2, 3. So at 1 pi over 6, that would be our typical intersection of the x-intercept, but it's been shifted up 1 unit. So instead of intersecting at the x-axis at pi over 6, we're actually going to intersect at 1. Everything's been shifted up 1 unit. Alright, and the same thing's going to happen here. If you count over 1, 2, 3, we're going to be at 1. Or sorry, we're going to be at 1, but that was the old x-axis. We just shifted everything up 1 unit. Okay, now remember, halfway between here and here, so we got 1, 2, 3, halfway between that would be 1.5. We were at, we go down, typically go down 1 and up 1. Well, we're multiplying it by 2, so instead of going down 1, we're going to go down 2, so we'd be down here. Alright, I'm at the halfway point between these two. So again, 1, 2, 3 over was the intercept. So 1.5 over is what we go up and down to get this number. I'm moving this far away from where we started. So we're going down 1, 2. Alright, same thing. 1.5. This is where I would be. I go up 1, 2 from there. Okay. So we're putting these plots at -1 and +3 instead of -2 and 2 because we're adding 1 to everything. So -2 plus 1 is -1. 2 plus 1 is 3. And so because we're starting at 1 instead of 0, we're getting different numbers for those whole number outputs. Alright, same thing. This -1 is going to occur 1.5 away from where that 0, or which has been shifted up to 1, occurred. So right there. And then if I go over 1.5 here, go up 2, and I'll be right there. Alright, and then same thing, we just connect our dots like we did before, and there's our period of this other tangent function. 2 periods, as it asks for us to do. Alright, and then again, I always think it's a great idea to check this stuff. So if I graphed y equals 2 tangent x minus pi over 6 plus 1. Alright, and then we graph that thing. I didn't adjust my window, but we'll be able to plot the points and see. Okay, I'm going to hit trace. At pi over 6, we should get 1. So if I type in pi over 6, I'm getting out 1. Alright, 2 pi over 6, 3 pi over 6, that's 5 pi over 6 divided by 2 to get the midpoint. So that'd be 5 pi over 12. I should get 3. So I'm going to type in 5 pi over 12, and I get out 3. Okay, so we're getting all the points that it looks like we're getting, so we've graphed it correctly. Alright, now cotangent. Cotangent is the reciprocal of tangent. So anytime the tangent function was equal to 0, cotangent is now undefined, and cotangent would then be have a vertical asymptote. So the tangent was equal to 0 at 0, so that means cotangent is going to have a vertical asymptote at 0. Tangent was equal to 0 at pi, so the cotangent is going to have a vertical asymptote at pi, right? And then 2 pi, right? So all the places that the tangent was equal to 0, you see vertical asymptotes now. Alright, now when the tangent was undefined, if you flip that over, that was because we were dividing by 0, so now we're dividing 0, which results in 0. So at pi over 2, 3 pi over 2, 5 pi over 2, the odd multiples of pi over 2, now we get intercepts. Alright, and what you also see is because we reciprocate, we flip over these values where it was above the axis, we're getting this downward pattern, alright, and in between 0 and pi over 6 or pi, the slope is negative once we get past pi over 2. So that's why we're dipping down in the negatives. If we flip over a negative number, if you reciprocate it like we are for cotangent from tangent, you take the reciprocal of a negative number, it's still negative. So we're going down into the negatives here. So it looks like the graph of y equals negative x cubed. It's kind of just been shifted over. And that's the cotangent function. And again, in between each one of these, we'll repeat that pattern over and over again. So it has that look to it. And the same thing as before, we get these 1s. In between, you take the reciprocal 1, you get 1. So we're going to get these 1s at pi over 4, 3 pi over 4. The odd multiples of pi over 4. We're going to get these 1 values that pop out right here. So we'll see those show up as well in the graph. Alright, we're going to do the same thing for cotangent. For variations of cotangent, it's just instead of negative pi over 2 and positive pi over 2, since the asymptotes are at 0 and pi, that'll be our place where we bound what's in between inside the cotangent function to get at our location of our new asymptotes. Alright, and then just like before, after you find your asymptotes, the intercepts are in between there. Halfway between the intercepts and the asymptote is a whole number point and another whole number point, not necessarily a whole number, just whatever a is. And you go up on the left side rather than down, and then down on the right side rather than up to get to those quarter points. Alright, so let's graph cotangent. So 3 cotangent 2x, I'm going to put between 0 and pi pi, I'm going to put in this 2x and divide both sides by 2. Well, if you divide 0 by anything, you still get 0. If you divide pi by 2, however, though, we get pi over 2. So our asymptotes are going to occur between, our one's going to be at 0, one's going to be at pi over 2. Alright, and then we can just take that first period and make as many asymptotes as we want. We just have to be pi over 2 apart. So there's another pi over 2, another pi over 2. We can just keep making as many of these as we want to. Alright, and then the same thing in the negative direction. Pi over 2, pi over 2, pi over 2. Just keep going left and right. Pi over 2, and you can make as many of these, like I said, as you want. Alright, now in between 0 and pi over 2, if I go halfway, I'll be at pi over 4. And at pi over 4, which is going to be halfway between these two, I will be on the x-axis. Make it a little bit bigger so the point actually shows up. Alright, now that's pi over 4. Now, the same thing over here if I went to the left side and in the middle of all these. Alright, again, I could keep going to the left, keep going to the right. But there's the zeros, and we haven't shifted left or right, so they are going to occur in the same place. We haven't gone up, so they're going to be on the x-axis. And now remember, this 3 is going to be the height above and below, halfway in between these two. Alright, now when these things aren't, when you don't have a grid that shows those halfway points, remember you can always use the fact that we can remove the pi and then just work with these numbers. So this is pi over 4 and 0, so we can tell it's going to be pi over 8 for that one. But what's the upper one going to be? So that's pi over 4, that's pi over 2. If we did the average of 1/4 and 1/2, and then divided that, change that back into a fraction. So that's 3 pi over 4. So at 3 pi over 4, oops, I'm sorry, I just added them, I didn't divide. Divided by 2, that's 3 pi over 8 when we change that back into a fraction. So at pi over 8 right here, at 3 pi over 8 will be that point right there. We're going to be at the points, right, because cotangent goes downhill between these. At pi over 8, we're going to be at 3. And then at 3 pi over 8, we're going to be down at -3. And we're going to do that same thing as many times as we want to. Halfway between the vertical asymptote and the intercept is where we're going to hit these 3's and these -3's. Alright, so we can make, again, as many of these as we want to. They won't have you quite make as many as I'm making right here. They'll have the grid kind of squeezed in a little bit, left to right, when the period's been adjusted like this. The period's been cut in half. Right. So anyway, we get that pattern over and over and over again. If you graphed it, so if you go into your catalog, second 0 catalog, you're in alpha mode. Let's go to C for cotangent. If you go to catalog and you scroll down, there's cosine. We just skipped over COT. There is no cotangent in here, and it's because of the fact that tangent and cotangent are reciprocals. So one thing you can do to get this thing to graph cotangents, you could put 3 divided by the tangent of 2x. Alright, and if you did that, I'm going to change my window, negative pi, that'll work, to pi over 2, that works. So if I graph this thing, there's what I'm seeing, okay, something similar to what we saw before. And if I trace, let's do, let's see, that would be pi over 2, so pi over 4, so negative pi over 4. I hit trace, negative pi over 4, I should get a, it's not giving me anything. That's right, it's not giving me anything because I'm writing it in there as tangent 2x, and we can't plug in pi over 4 into tangent because that causes division by 0 within the tangent, even though it doesn't here because of the reciprocal nature. So if I get something really close to negative pi over 4, so like negative pi over 4 plus 0.0001, now we can see we're really, really close to 0. So that point is correct. If we pick these numbers in between there, so that would be negative pi over 8. That's going to get us down to that negative 3. Alright, and again we can see if we plug in those numbers, pi over 8, we can see that we've graphed it correctly, just using this to verify. So there's the positive 3. Alright, so there's a graph of the cotangent function. Just remember it's flipped over from the tangent. We've got to get the higher point going up to the left and down to the right to get this number that's in front of cotangent.